Alrighty, so let's talk about Dalton's Law. Dalton's Law is going to be applied if we have a mixture of gases and we actually care about separating the gases out from one another. If you remember, in the previous video we talked about how most of the time we actually don't care. If we have a mixture of gases, like in atmosphere, for example, where it's 70-something% nitrogen, 20-something% oxygen, 1% argon, and a bunch of other stuff, most of the time in that situation, we don't actually care that there's other gases, because they're all going to behave the same way. But sometimes we do care. Sometimes we want to know exactly how much of the total pressure is caused by one part of the mixture, for example. And so when we're interested in something like this, when we want to separate out the gases, or if we are given separated gases and we need to put them together, either way, we're going to use Dalton's Law. And what Dalton's Law tells us is pretty straightforward. It is simply that if you take all of the partial pressures, so all of the pressures caused by the individual components of a mixture, adding those together will give you the total pressure. Pretty straightforward. Essentially, the total is the sum of the parts. Essentially, if you add together all of the different parts of the pressure, you will get the total pressure. So these partial pressures, once again, this is the pressure that is exerted by only that individual component of the mixture. So every individual component of a mixture will have its own partial pressure. So the partial pressure is not referring to that you're looking at just a section of that one molecule. You're saying that this is a part of the total. So every molecule is making up a part of the total pressure, and so that is the partial pressure. So for example here, and actually let's do the second example here first, because it's actually a little bit easier. A mixture of helium, neon, and argon has a total pressure of 558 millimeters of mercury. If the partial pressure of helium is 341 millimeters of mercury, and the partial pressure of neon is 112 millimeters of mercury, what is the partial pressure of argon? So we're told we have a mixture of 3 different noble gases, and we're asked to find the partial pressure of one of them. So go ahead and pause the video and try to work this out on your own, and we'll work it out together here in just a second. Okay, so because we have a mixture and we're asked to investigate just one part of the mixture, we are going to be using Dalton's Law. So the total pressure is equal to the pressure of the argon plus the pressure of the neon plus the pressure of helium. So we're told in the problem that, let's see, the total pressure is 558. Oh, why did I put 555? 558. And I'm just going to leave the units out for now, just because I don't want to write millimeters of mercury 5 times. So we have 558 is the total. The partial pressure of helium is 341. Neon is 112. And we're asked to find the partial pressure of the argon. So this is going to be just a simple subtraction. That's all this is. We know the total is 558, and we know these 2 parts. And so if we subtract those 2 parts from the total, so 558 minus 341 minus 112, that leaves us with the partial pressure. Go away. It's not supposed to pop those up while I'm in here. The partial pressure of the argon is 105 millimeters millimeters of mercury. All right, hopefully that makes sense. Again, it is just the different parts are the sum of, the total is the sum of the different parts. So let's look at that first example that we skipped over just a second ago. So this asks us to calculate the partial pressure of oxygen that a diver breathes with a heliox mixture containing 2% oxygen at a depth of 100 meters, where the total pressure is 10 atmospheres. So if you want to pause the video and try to work this one out on your own, you can do that now. So this one is a little bit different than what we did in the last example, because it's not just saying we have different parts and add them together and subtract to get the one missing part. This is a little bit different, but in reality it is essentially the same thing. It just looks very different. So just a couple of quick notes here. When it says a heliox mixture, if you've ever gone scuba diving before, that's what they give you, is a heliox mixture. I've actually never gone scuba diving before, but I've read, anyway, that what they give you is a heliox mixture. That's a mixture of helium and oxygen. So you have helium and oxygen. The oxygen, obviously, because you need to breathe. You need oxygen to live. And then they give you helium. I'm not actually sure why they do helium instead of nitrogen, but the helium is just essentially inert. It's a placeholder, essentially. It's there to increase the pressure so that the high pressure of the ocean doesn't crush you, but it's not really doing anything, chemically speaking. So we're told that our mixture contains 2% oxygen, and when we're at 100 meters, we're going to have a total pressure of 10 atmospheres. And we're asked to find the partial pressure of oxygen in that state. And so really what we're trying to do here, even though it's not immediately obvious, is we're actually just trying to figure out what's 2% of 10 atmospheres. Because we're always going to have 2% oxygen. The only thing that's changing is the total pressure. So the amount of helium that's in the mixture and the amount of oxygen in the mixture are going to be changing, but the percentage is going to stay constant. There's always going to be 2% oxygen and 98% helium. So if we have 10 atmospheres, there's a couple different ways that we could do this. We could just take this number and multiply it by the decimal form of 2%. So if you remember how to convert from a percentage to decimal form, you essentially just divide by 100. So we'd be moving the decimal point over 2 spots. And so that will be 0.02. That is the decimal form of 2%. So again, that's just dividing by 100 is how you do that, which ends up just moving the decimal point 2 spaces to the left. And so we could just take this and multiply it by 0.02, and that will tell us that the partial pressure of the oxygen is 0.2 atm. Which is the reason why we use 2% oxygen, by the way, to get that 2 atmospheres. And actually, I think what I told you a minute ago is not correct. I think I told you that that percentage stays constant. Actually, now that I think about that, I don't think that's correct. I think the percentage does change. Actually, I know the percentage does change, so I apologize for that. So this is only true at 100 meters. It would change as you go up and down. What doesn't change is this number, actually. So this partial pressure would stay constant, and it needs to stay constant because 0.2 atmospheres is essentially what we have in atmosphere right now. What you're breathing is actually 0.21, I believe, atmospheres of oxygen. So this is the number that stays constant. The 2% does change. So I apologize for misstating that earlier. The other way that we could have done this, by the way, If you prefer to think about things in terms of conversion factors, you could do this as well by looking at this and saying, okay, if we have 2% oxygen, that's the same as saying, for every 1 atmosphere of the entire mixture, we would have 0.02 atmospheres of O2. But in this case, I don't really think that's an easier way of doing it. It's almost like adding an extra step even. So while this would work, so you would cancel out here the atmospheres of the whole mixture and be left with atmospheres of O2, I don't really think that that's going to end up giving you, I don't think that's going to be an easier process. So I wouldn't actually suggest that doing it this way, but it would work. It still ends up giving you the 0.2 atmospheres. All right. Moving on then, let's talk about gases in chemical reactions. So we can use our knowledge about the behavior of gases to solve problems involving gases as reactants or products. So we have an example here where we're asked how many liters of oxygen gas sorry, that's a typo there, not from. Obviously, I was not paying close enough attention when I typed this in the other day. Form when 294 grams of potassium, let's see, that'd be potassium chlorate, completely react in the reaction that's shown there. Assume the oxygen gas is collected at 755 millimeters of mercury. Let me see, did I give myself a space to do that? Yes, okay. So, and actually, yes, this is the same thing here. So, and I mistyped that again. I think I actually probably just copied and pasted that. Alright, so we're told 294 grams of potassium chlorate are reacting in this reaction, and we're asked to figure out how many liters of O2, and that should be a subscript, by the way, O2, are going to form. Same thing here. Sorry about all the typos there, but yeah, that should be subscript of 3. So if you're interested in trying to work this one out on your own, go ahead and pause the video here. Think about it for a minute, see if you can work out what we're going to do, and then come back and we'll solve it together. Alright, so we're asked to find the number of liters of O2 that's going to form. If we're going to work that out, we're probably going to use this equation, because we're not told that we don't have a sample of gas that we're heating or cooling or anything like that. We're just making an amount of gas. And I know that's not immediately obvious that what we're doing is we're dealing with what's the word we used? Stagnant's not the right word, but a sample of gas that's not changing anything. But that is what we're going to work out here. If we're going to try to find the liters, which will be the volume here, we're going to need the pressure, the number of moles, and the temperature. Now, I don't believe... we're not given the temperature here, and we are going to need the temperature. Hold on just 1 second. I copied this from the book. And I wonder if I accidentally left out the temperature. So if you tried to work this out, if you paused the video and tried to work this out, I apologize for not giving you all the information that you needed. Okay, let's see here. Yeah, I just left that out. I apologize. I don't know why I did that. Boy, I'm apologizing for a lot in this video. So the temperature is 305 Kelvin. And that was just given in the problem. This is example 1111, I believe. And it was just given to us in the problem. So we need to know the temperature, the number of moles, and the pressure to be able to solve for V, because we always know what R is. It's just a constant. We are just given the temperature in the problem. We are also just given the pressure. It's just right there. It's 755 millimeters of mercury, which I'm going to go ahead and convert to atmospheres, because I know I'm going to need atmospheres later so that it matches what's in R. And if you remember, to convert to atmospheres from millimeters of mercury, you divide by 760, because there's 760 millimeters of mercury in every 1 atmosphere. And so this is going to be 0.993 atmospheres is the pressure. So the only thing that I have left to find is the number of moles. And that is where the stoichiometry here is going to come into play. Because we are told we have 294 grams of potassium chlorate, and we're given the balanced chemical equation, so we can use stoichiometry, if you remember from a previous chapter, to work out, given this much potassium chlorate, how many moles of O2 will be formed. In the examples we did in the previous chapter, we would usually do a mass to mole to mole to mass conversion, but in this case we're actually only going to go to that second number of moles. We actually don't need the mass of O2. We just need the number of moles of O2. So we're only going to go to this second number of moles. So let's go ahead and work through that here. So we have 294 grams of KClO3. Oops, I put the 3 in the wrong spot. Sorry. All right. To get from the mass of KClO3 to moles, we would need the molar mass. So if I add up all 3 of those atoms, well, 5 atoms, so we have 3 oxygens, so 3 times 16 for the oxygen, 35.45 for the chlorine, and then potassium is 39.1. The molar mass of that molecule is 122.55 grams for every mole. And then we have one more conversion, so that was going from here to here. We have one more conversion to go to moles of O2, and that's using the balanced chemical equation here, which, sorry, I kind of crossed out the 2 there, but then we have, for every 2 moles of the KClO3, we will have 3 moles of O2. So my grams of KClO3 cancel, moles of KClO3 cancel, leaving me with moles of O2. So if I do that math, 294 divided by 122.55 times 3 divided by 2, we will make 3 let's see, we get 3 sig figs, I guess, 3.60 moles of O2. And actually, I shouldn't have done sig figs there yet. We do sig figs at the end, but oh well. So 3.60 is the number of moles of O2. So that is that number. So we now have everything that we need. So I'm going to go ahead and do the algebra first here. So I'm just going to divide both sides by P. So we have the volume is equal to 3.6 moles times 0.0821 liter atmospheres per mole K. So many units. 305 Kelvin divided by 0.993 atmospheres. So close to 1, but not quite. Alright, so 3.6 times 0.0821 times 305 divided by 0.993. We will make 90.8 liters of O2. And I believe we actually do this reaction in General Chemistry 1 in one of the labs that we do. We take potassium chlorate and we just heat the crud out of it. And when you do that, you actually force the oxygen off of the molecule. And so we make a whole bunch of oxygen, apparently. A very large volume of oxygen when we do that. Although we don't normally do it with 290 grams of potassium chlorate. It's closer to 10 grams, so not quite so much. But that is pretty much as intense as these problems are going to get. Well, not pretty much, that is. It's not going to get any more intense than that. That is combining a couple different topics from different chapters, and so that is really the most complicated we're going to do, because that is a synthesis of different ideas together. And so that is, if you can figure out, if you can work your way through a problem like this, you should be able to work through anything that I could throw at you from this chapter. Alright, so the last thing here, just a brief note about what we call standard temperature and pressure, because when you come across some problems in the homework, you will probably see what's called STP mentioned. And what standard temperature and pressure are, this is just as the name implies, a standard temperature and pressure that people will often run experiments at, just to make life easier, essentially, so you don't have to constantly be saying, I'm at this temperature, I'm at this pressure. You can just say at STP. And if you don't really care what the temperature and pressure are that you run a reaction at, people often do it at STP just to make their lives easier later on. When they want to go back and either reproduce things, or they want people to be able to reproduce the work that they did. So STP is referring to 0 degrees Celsius, which is 273 K, and 1 atmosphere of pressure. So if you have a practice problem and it says you're at STP, that's what it's telling you. It's telling you the temperature and pressure. You're at 1 atmosphere of total pressure and 273 Kelvin. One situation where this is kind of nice is if you're at STP and all you're trying to do is convert between the number of moles of gas and the volume. You can use this little shortcut here, where if you're at STP, you actually have a conversion factor between moles and volume. No matter what gas you're dealing with, if you're at STP, 1 mole of that gas will occupy 22.4 liters. And so sometimes that might be handy where you can go back and forth easily. This is not something that you have to know, because if you know you're at STP and you know you have 1 mole of the material, you have enough information where you could plug that stuff into the ideal gas law and be able to find the 22.4 liters that way. So it's not something that's you have to know, but it is a shortcut, essentially. If you can remember it, it can keep you from doing a little bit of work. All right, that is it for this chapter. Please be sure to be working through the homework as soon as possible after finishing the videos here. And obviously feel free to be rewatching the videos as you work through the homework if there's something that's not clear. And I will talk to you all later.